Thank you. Do I have audio? Yep. All right. Most of you know the drill from last semester. Don't the rest of you make a point of signing in every class. If I forget to pass around the sheet, someone remind me. Like last semester, I do keep attendance because the university requires it. I do not know or care why. They do. So I keep track of attendance. I do not give you a grade for attending. No participation grades, no participation trophies. If you want a participation trophy, join Little League. You want a trophy in this class, you got to win, place, or show. You know, most of y'all remember me from last year. This is the part where I give the big barking speech about how hard-nosed I'm going to be, and most of you know what a lie it is. I'm not. I'm going to bend over backwards to give you every point I can find an excuse to give you. I'm going to do whatever I can to get you through this class with a passing grade. And that's what I do. That's my job. But every point you get will be because you demonstrated that you learned something of the material that we cover in this class. Okay? You're grown adults. You don't need to call me and get permission if you're going to skip class. You know, you're paying to be here. You're grown adults. You don't need my permission to skip class if you want to. But if you skip class, as some of you may recall from last semester, it's going to be a bear to make up to pass the course if you don't attend the lectures. So, you're all grown adults. Make your own decisions. Go through the syllabus, talk about the grading. Those of you from Physics 1 may notice that I've changed the grading just a little bit. All that labs were worth 24 points, and the homeworks were worth 7 points, and one exam was worth 100 points, and another exam was worth 120. 6 exams, 100 points each. That's 600 points total. 14 homework assignments, one assignment each week. They're worth 20 points apiece. 14 labs, one a week, 20 points apiece. That's your grade. Don't miss the labs. Making up labs is hard. I mean, it's not that I won't do it if we can, but it's hard to do. They take time to go through and work them. And it's really about the easiest 20 points you're going to earn in this class. Because that's as close as you're going to get to a participation grade. I think seriously, if you show up and you do the work, you don't get graded for whether you get the right answer or not. I don't care how many percentage points off you were and how much percentage error you got. What I wanted to see is that you came in and you conducted the experiment and you got the results. You do that, you get the 20 points. I'm not going to grade you on how accurate you were in your measurements. Well, the homework, late work. You know, most of you remember from last semester, I accept late work, and in the syllabus it says I can deduct up to, I might deduct up to 10% per week for late work. And those of you from Physics 1 know that I didn't deduct any late points from anybody. It's not my goal here. It's not to take away points from you. My goal is to give you as many points as we can justify you getting. Okay? But in this, there's got to be some, I will work as hard as I can to get you through this course. learning the material and passing with as good a grade as you can get. But you have to work with me. I'm going to require that you work as hard as you want me to work for you, with you. All right? So, I'm not going to threaten to take points off if you turn in your work late. If you turn in your work late, sure, I'm going to accept it. I will tell you what I did last semester, that if it comes in late, I may grade it if I get the chance. The later in the semester we get, the more likely it is that a late homework just won't get graded. So turn it in on time, and it will get graded, and you will get credit. You will get credit. And the only thing I'm going to ask of you is that you don't mistake my being nice about this with license to just walk all over. Okay? Because if I get the impression at the end, and I understand how it works, is the other professors don't like to admit that they're lying when they talk about how tough they're going to be, and you turn in the paper on time or you don't get credit and blah, blah, blah. Okay? Maybe they do that and maybe they don't. I don't know. I don't manage them or supervise them. But I do understand that when one instructor says he's willing to accept the work late, and another one says they're not, guess which one's going to get the work turned in on time? If I get to the feeling like y'all are taking advantage of me and y'all are backloading my semester with a pile of work that I'm going to be buried under trying to catch up by the end of the semester, my niceness can and will end abruptly. All I'm asking is y'all work as hard with me as I work with y'all. And we can all get through this course. And with passing grades and with good grades for some of you. Those of you who remember the bonus points on the homework assignment, not going to do that again. I'm just not doing it because, frankly, the only people who racked up all these bonus points were the ones who didn't need them. And the ones that would have benefited from them didn't. So it was not an effective mechanism for getting people through this course. I'm going to focus my efforts where they can do the most good. What else? Exams in class are proctored closed book exams. You cannot use your notes. You can't use your book. You have to do the exam with what you know, what you learned. Now, what you do get to use is a calculator, because I'm here to teach you math, not arithmetic. So use the calculator to do the arithmetic. Just make sure you're doing the math, because the calculator will lie to you. Some of you might remember that from last semester. Index card. You will get to use an index card for the exams. Standard size index card. But you're only allowed to use one side, the outside. You can use the front side, you can use the back side, you can write on the edges if you can read it. But you're only allowed to use the outside. You may not split the card in half and use the inside too. That was supposed to be kind of fun. Yeah, no. No. Don't, yeah, again, no. Use an index card, not a 3 foot by 4 foot index card. Now, depending on how the schedule goes and how many days we have to miss because of tornadoes and rainstorms, how much I still have to cover by the end of the semester, I may end up giving one or more of those exams, especially toward the end, as take-home exams, at which point they become open book, open notes. But I'm telling you now, if you take it home and when you ask Google to do it for you, make sure you write down all the steps Google went through to come up with whatever answer they gives you to write down. Okay? Here's another thing that's going to be a little bit different than last semester. Who can tell me what this stands for? No work, no credit. Again, this isn't like a hard and fast rule. I'm not going to mark it wrong if you put down the right answer. Maybe. Okay. Like I've said, and most of you know, I will bend over backwards to give you as many points as I can come up with an excuse to give them to you. But every point I give you will be because you demonstrated that you learned something of the material. You write down all the answers, and that's all you write down, and as long as they're right, yeah, I'll give you credit for it. But if the decimal point is moved, if you missed a minus sign, then it's not the right answer. And if you didn't give me any, if you didn't show me any work you did to get that answer, there's nothing for me to go by to give you partial credit for. So if all you write down is the answer, you take your chances. It is in your own self-interest to show me the work you do to come up with that answer. Because that's what I'm going to look at when I try to figure out how much credit, how many points to give you for that, for what you did do. Now here's the one exception where I actually am going to become that hard-nosed, unreasonable, intransigent, you know, you're all intelligent young men. And those of you who don't already know will quickly figure out that all the odd problems have the answers written in the back of the book. So, when you find that you're pressed for time and you just can't do the homework, and you're tempted to just go to the back of the book and write down the answers, you better write down the answers for the even-numbered problems too. Because when I get homework, and this happens, it happened last semester, when I get the homework turned in and the only thing I get are just the answers to just the odd-numbered problems, you ain't getting credit for none of it. Ain't going to happen. You can't do the work, you can't have the credit. So, do we have any questions? No? All right. Let's get started on our physics. In Physics 1, in the first one, we studied largely mechanical forces, motion. We did get into field forces to the extent that we also looked at gravity. And gravity is a field force. And it also introduced us to the whole idea of conservative forces and the conservation of energy. But gravity is not the only field force. This semester, we're going to pick up where we left off. We're still looking at field forces. Now we're going to look at electric and magnetic field forces. And at some point, what we're going to discover is that they're actually very closely interrelated with each other. So, how many of you are already familiar with electricity and electric charge? Okay, good. We're still going to take this kind of step-by-step, rudimentary, one step at a time, as they say. And we're going to and this is our first lab that we're going to do tomorrow. This is on electrostatic forces. So, let's start by talking about what is static electricity. What is the electric charge? So who wants to answer that? Who wants to tell me what is static electricity? But you, yep. Well, you're bumping right up against it. There you go. Think of the words. Take the statement one word at a time. Static electricity. What does the word static mean? Stationary, not moving. That's exactly what static electricity is. It's electricity that's not moving. It's static. Everything. Who can tell me the fundamental particles that everything in the universe is made up of? In order of descending mass, start off with your neutrons, then you've got your protons. The next lightest is the electron. What's the next lightest fundamental particle? I'm sorry, I completely messed this up because I was going in the wrong direction. Starting with the lightest, the least massive to the most massive of the fundamental particles. You start off with the photon. Then you've got the electron. 1,800 times more massive than the electron, you've got the proton. A little bit more massive than the proton is the neutron. And the most massive of all the fundamental particles is the moron. We're going to look at the electrons and the protons for right now. We might deal with photons later on. As Dalton was pointing out, you rub things together, electrons transfer from one object to another. In fact, that's how electricity was discovered. Please do not ever say, or certainly don't ever let me hear you say, that Ben Franklin invented electricity. Okay, he did not. He didn't actually even discover it. He just kind of proved that lightning was electricity. Okay. But he did make one major contribution. I don't know how major it was, but he made one contribution, a legacy that lives on to this day. The field of electricity. Electrons are negatively charged. Protons are positively charged. How do we know that? What does that mean? Y'all have studied electricity. What about solid state electrons? Anybody, y'all studied the solid state, p-n junction, electron flow, hole flow? Well, did you know that we have empirically proven that it's actually the hole flow that does the work, not the electron flow? You know how we prove that? It's the holes carry the smoke. If you let the smoke out, it quits working. You people need to get off the being so serious. I mean, I'm using some of my best material, and y'all aren't even cracking a smile. That kills over in the electronics building. Seriously, why is the electron, what does that mean that the electron is negatively charged and the proton is positively charged? No wrong answers, just guess. Give me your best guess. What do you think that means? Yeah, you're got it backwards, but you're exactly right, except backwards. They don't repel each other, they attract each other. Negative charge attracts positive charge. Negative charges will repel other negative charges. They will be attracted to positive charge. Positive charges will repel other positive charges and be attracted to negative charges. So, how do we know which one's positive and which one's negative? Where's the zero? And what constitutes the zero? Well, the zero is the neutron, because it has no charge. Well, why is the electron on the left side of the neutron and the proton on the right side of the neutron? The answer is it was a completely arbitrary choice. It doesn't matter which one you call positive and which one you call negative. In fact, the whole idea of positive and negative from a strictly mathematical perspective may or may not be true. We don't. All we really know is that electrons repel other electrons and they attract protons, and vice versa. We know that the quantity of charge that they both have is the same. The symbol we use for it is E. Who knows how many, what are the fundamental, what are the units of electric charge? Can y'all read this, or am I writing too small? Coulomb. How many Coulomb is one electron? It's 1.602. That's 10 to the minus 19 Coulomb. Somebody look that up. Should be on your front cover. There it is, charge of an electron, 1.60 times 10 to the minus 19 Coulomb. Yeah, 1.602, and it gives it to you to a bunch of decimal places. It's the charge of an electron. Specifically, for an electron, it's minus 1.602. For a proton, it would be plus 1.602 times 10 to the minus 19 Coulomb. That's where the positive and negative signs come in. The charge E is equal to 1.602. That's the fundamental charge. And you're never going to ever find anything with a smaller charge than this. You can't have a fraction of one of these fundamental charges. Any of you ever go and major in physics, one of the experiments you're going to do in the upper level undergraduate courses is called the Millikan oil drop experiment, where you will make a measurement and you will actually measure that value and find out that you're never going to get a fractional quantity of electric charge. That is the charge on every electron. It's the charge on every proton. Now, Dalton was talking about when you rub things together, you can transfer electrons from one object to another. And this is actually a rather persnickety little process. It depends on so many things. Humidity, lots of moisture in the air, makes it very difficult to do the experiments we're going to do tomorrow. So if we come in tomorrow and it's very humid, we may discover that some of these experiments don't want to work well at all. We come in on another day of the week when it's nice and dry out, there's almost no humidity, and basically anytime you walk into a room and you can't touch the doorknob without getting shocked, on those days there's lots and lots of static electricity to be had, and these experiments we're going to do tomorrow, they work beautifully. Book talks about something called the law of the conservation of charge. Okay, what all they're really saying is that you have this fundamental quantity of charge, and every object has atoms, and the atoms have electrons, and you cannot make new electrons, and you can't destroy old electrons. That you can rub things together and electrons will transfer from one object to the other and build up a static charge. Why do you imagine that that doesn't happen as well as readily when there's lots of humidity in the air? No. Yeah, you're getting closer. Think about the water molecule. You got a pair of hydrogen atoms and an oxygen atom, and they're bound together. The water molecule is what's called a polar molecule. And believe it or not, water is one of the most powerful solvents you're ever going to experience or ever going to come across in this world. It is an extremely powerful solvent. Because on one side it gets negative and on the other side it gets positive, and it creates a dipole. And it produces a dipole, an electric. So there's a net difference in potential from one side to the other. That means that this side of the molecule is very attractive. And I mean that literally. I don't mean like as in wolf whistle, woohoo, attractive. I don't mean it's, I mean it will attract all those negative electrons. So if you're walking around in a room full of air that's full of lots of water vapor, every molecule of water is there sitting there ready to suck up and to attract and carry off that extra electron that's just floating around on the surface somewhere. And that's why when there's high humidity, these static electricity experiments become very difficult to do. And they don't always work right in high humidity conditions. What they discover, I want to say Ben Franklin. There were others who did these experiments as well. In fact, the earliest experiments went all the way back to ancient Greece and even into ancient Egypt. Matter of fact, what they discovered was that if you rub, everybody know what amber is? Fossilized tree sap. It's where they make dinosaurs in Jurassic Park. Right. Well, it turns out that they discovered that if you rub amber on rabbit fur, that it will develop an attractive force. What? Somebody remember to remind me that my phone is over there so I don't walk off and leave it. I don't want your friends interrupting our class. I don't want my friends interrupting our class either. What happens when you rub the amber and the rabbit fur together is it picks up electrons. They've developed, they're attracted to the surface of the amber, and it develops a charge. The fur gives up all these electrons quite easily. The point is that when you transfer electrons from one object to the other, the total charge is still conserved. So if you have two objects, two pieces of film or fur or whatever that you're working with, and you charge them up by rubbing them together, if one develops a negative static charge, then the other one is going to produce an equal and opposite positive static charge. Because for every electron you take away from this first object and deposit on the second object, the first object is left with a net proton positive charge. And that's what they mean in the book when they talk about the conservation of electric charge. If you go on page 16, page 445, there it shows you a diagram of that water molecule. Now, let's do some thought experiments. These are the ones that we're going to be confirming in lab tomorrow. What happens if you take two metal spheres or two anything, and you draw, somehow or another, you draw a bunch of electrons off of this one and transfer them over to this one. Then whatever charge you would draw off of this one onto here, you're going to leave behind the positive charge on the other. Conservation of charge. If that is a conducting surface, not an insulator, but if that's a conducting surface, like say a metal sphere, what's going to happen to all these electrons? They're going to repel each other until they redistribute across the surface of that conductor uniformly. So they will put as much distance between each of them as they can. The same thing will happen over here. To the extent that the protons are free to move, they will want to move and repel away from each other also. It doesn't always work as efficiently with protons. Why might that be? Think of it as a metal sphere. Why might all those protons not redistribute themselves around the surface of that sphere? What are the protons? Protons are the nuclei of the atoms. Okay? Remember, this is you've got your nucleus of protons. If you've got 3 protons, you've got 3 electrons. And yes, those are all little e's. Well, when you take one of these electrons away and put it over here, on this sphere, now this one has one more proton, so it has a net positive charge. This one has one more electron, it has a net negative charge. Now think about this sphere. All the excess electrons are on top of this sphere sitting on the surface. They're going to redistribute. They're going to repel against each other. They're going to redistribute themselves to put as much distance between each of them and all the rest as they can. Why won't the protons do the same thing? Because not that they have to stay together with each other, but they are the nucleus of the atom. And in a metal, or in most objects, the atoms are not really as free to move around as an electron would be. Electrons move by transitioning from one atom to the next. The atoms themselves are kind of stuck in the structure. They're stuck in place, in the lattice, in whatever structure they're in. Whether it's crystal, or in case of metals, it's usually a crystalline structure. But the atoms are not really free to move. Now, if it's a gas, then obviously the atoms can move around freely. And in that case, then the positive charges would in fact redistribute themselves throughout the gas. But we're not going into plasma physics here. So in the case of this conducting sphere, the atoms aren't free to move around, so the protons aren't going to redistribute. Now, what they might do, and in fact in the conductor what they will do, if they can, is this proton will strip off of an electron from an atom nearby. And so eventually, the electrons on this sphere are going to redistribute themselves to distribute the potential, the charge, as evenly as they can also. It just won't happen as fast with this as it does with the electron. Okay? Now, you've got these 2 conducting spheres and they're charged. This one's charged positively, this one's charged negatively. Now you take a nail, you lay it across both of them. What happens? The nail is a conductor, and it conducts all of these excess electrons right over here to where they can fill up all of these open positive, all these positive charged ions. But yeah, the electron, the charge will then migrate through the conductor over and redistribute, and it'll even itself out. So basically what you'll do when you short them together is you discharge the static buildup. They drew a picture of this on 445 as well, page 445. Now, let's look at 16.4, because this is one we're gonna look at tomorrow in the lab. So I really did want to cover this today. We've got this electroscope, and instead of trying to draw you a picture of it, I'm just going to get one out and show it to you. Handle it gently. Do not let the glass slip out and break. But pass it around, y'all can look at it. You're going to get to work with one tomorrow. What happens is you build up a charge on a rod or a piece of acetate or a piece of, with a fur or something. You build up a charge and you touch that sphere on top. What happens when you've got both of these foils hanging down here and they're neutral, they're not charged, and you've got a rod that's got all kind of extra electrons built up on it. What's going to happen to those electrons when you touch that sphere on top of that electroscope? They're going to try to they're going to look to redistribute themselves to put as much distance between each of them as they can, which means they're going to quickly migrate down this. Not all of them, but a lot of them will migrate down this rod and they will start building up on these two foils. And when that happens, what happens to those two foils that are hanging there? They get charged with electrons, they spread out. They repel each other. And the two foils will separate. You then come back and touch this with something, touch it again with something that will give the electrons somewhere else to go. They'll draw up and back out of that electroscope, and the two foils will come back together. The other thing we're going to do in lab tomorrow, we're going to look at the Coulomb force. We're going to see that if you charge up one object negatively and you charge up another object positively, then the two objects are going to repel each other. They're actually going to produce a force called the Coulomb force. It's written, the equation for it is written out here on page 447. The equation 16.1. Coulomb force is equal to, what do they use? K is the constant they use? Yeah. K times Q1 times Q2 divided by R squared. Just R, right? It is R squared? Thank you. Divided by R squared. Q1 and Q2 are the two charges. You can actually calculate, you got to know what K is. I think it's 4 pi times 10 to the, no, not 8.988 or 9 times 10 to the 9. Newton meter squared per Coulomb squared. And we're going to look more into the Coulomb, into K and the Coulomb force, and we're going to do some calculations with it as well. But in lab tomorrow, what you're going to be looking at is that when you get two things that are charged up together, when they're charged alike, then they're going to repel each other. If you get two things that are charged opposite, they're going to attract one another. It's all going to be very qualitative. Y'all do know the difference. Y'all know the difference between qualitative and quantitative, right? Okay. Y'all take chemistry? No? Well. Tomorrow we're going to be looking at qualitative analyses, just how the things behave under various conditions. And the This is one thing I do want you to keep in mind for tomorrow, and that is the arbitrary nature of positive and negative. Okay? I told you this was Ben Franklin's one contribution to the field of electricity. He was the one, when he wrote his papers, that assigned quite arbitrarily the negative sign to the electron and the positive sign to the proton. Okay? That's why we still call the electron negative and the proton positive. Fact is, if we were, if we decided that we're going to change it and do it just the opposite, it wouldn't change anything. It's just an arbitrary designation. But once we quantify, I would erase it, but once we quantify that charge and give it units of coulombs, then the sign does come into play when you have negative charge versus positive charge doing the math. But the math would still work out exactly the same if we did go in and reassign the charges to the opposite signs. So, one or more of you may end up finding yourself wondering tomorrow, why? How do I know which one is negative and which one is positive? Which one's got the extra electrons and which one's got the extra protons? The fact is, without more instrumentation and more definitions, you really aren't going to be able to. And that's why, it's because it is all very much arbitrary. Did everybody sign the sheet? Anybody think of anything that I've not covered? Any questions? No? Well, then we will pick up here on Friday, but I will see all of y'all tomorrow for lab.